Hi everyone, it's Mrs. Meehan, and in this screencast, I'll be going over power. It is often important to know not only if there is enough energy available to perform a task, but also how much time will be required. This brings us to the concept of power. Now, power is defined as the rate that work is done, or you could say that energy is transformed. So the equation for this is power is equal to work over time. Since work is measured in joules and time is measured in seconds, the unit of power is the joule per second. But in honor of James Watt, who made critical contributions in developing efficient steam engines, the unit of power is known as the watt. Now let's take a look at a couple different types of light bulbs. So in the past decade, we've been phasing out the use of incandescent light bulbs. And this is because they use a lot more energy. Here's an example where it's 60 watts of power for this incandescent light bulb. So what this means is that it converts 60 joules of electrical energy to heat and light every second. Compared to this LED, um, so it's the same light output, but it's provided by a 9-watt LED bulb, and it's converting 9 joules of electrical energy to mostly light and very little heat every second. So this is a much more energy efficient technology, and it takes a lot less energy to run. Now, what power companies will do and how they bill your parents or guardians, they bill residences and businesses by how much energy they use. So the energy used is found by multiplying the power of the electrical devices by the time it is consumed. Now, the unit that they will use is called the kilowatt hour, where a kilowatt is equal to 1,000 watts. As an example, and it's also a good example of unit conversion, let's take a look here. So we have a 9-watt LED bulb, so the much more efficient option, operating for 6 hours a day for a 30-day month. It would consume, let's take a look. So we have our 9 watts. Now we want to convert it to kilowatts. So there's 1 kilowatt and 1,000 watts, or 1,000 watts in a kilowatt, and then multiplied by the 6 hours in a day. So what you notice here, and times 30 days, we have watts canceling out here, and you have days canceling out, leaving you with the kilowatt hour. So in this example, it is 1.62 kilowatt hours to operate this particular bulb 6 hours a day for a 30-day month. Now, let's assume that the average cost of a kilowatt hour from the power company is 15 cents. So you have 1.62 kilowatt hours times 15 cents per kilowatt hour gives you about 24 cents to operate that one light bulb for a month. Now, with the incandescent bulb, it would be a bit more than that. And then you have multiple light bulbs in your house, so you can see that it could add up over the course of a month. So significant savings with this LED technology versus incandescent. Now, there are a couple different expressions to use for power depending on what you want to solve for. So we have our base equation. So power equals the work over time. Now we know that work equals force times the parallel displacement. So you could technically sub in the force times displacement for work, and that gives you an equation of power equals force times displacement over time. Now, if you write it slightly differently, or if you just take a closer look, you'll notice that we have displacement over time here in this part of the equation. Now we know that distance over time is actually the definition of velocity. So you could technically write the equation and take this further and say that power is the force times velocity. So a few different things that you can solve for here. So power can be defined as the product of the force applied and the velocity of the object parallel to that force. So that's one expression that you could use to solve certain problems. And then there's also one other. So we've talked about how initial energy plus any additional energy, the work done, is equal to the final energy. So another definition for work is that work is equal to the final energy minus the initial. So we see this down here. So since we could define work as the final energy minus the initial energy, you could sub that in for work in the power equation. So we have power is equal to the final energy minus initial energy over time. So the power absorbed by a system can be thought of as the rate at which the energy in the system is changing. So three different expressions. We have the base equation of power equals work over time. You also have the other expression here where power is equal to the force times the parallel velocity. And this third expression where power is equal to the change in energy here, final energy minus initial over time. So three different expressions, and you can solve for many different variables using them. So let's try out a couple practice problems here. So steam engine does 50 joules of work in 12 seconds. What is the power supplied by the engine? Okay, so we can just use the base equation here. Power is equal to work over time. Since you are given work and you're given time, so 50 joules divided by 12 seconds gives you 4.166 joules per second, otherwise known as the watt. So this letter D would be correct. How long must a 350 watt engine run in order to produce 720 kilojoules of work? So here we are given the power, 350 watts, and we are given work, 720 kilojoules, which if you convert it is 720,000 joules because there's 1,000 joules in a kilojoule. You just rearrange the power equation. Power is equal to work over time. If you solve for time, that is equal to work over power. So 720,000 joules divided by 350 joules per second, or watts, is equal to 2057.14 seconds. So letter D. Okay, next one. How long must a 350 watt engine run in order to produce 360 kilojoules of work? So again, we are given the kilojoule, so we need to convert that. 360 kilojoules is 360,000 joules. And again, time is equal to work divided by power. So 360,000 joules divided by the 350 watts, or joules per second, gives you 1,028.57 seconds. So letter C. Next question. A 12 kilowatt motor runs a vehicle at a speed of 8 meters per second. What is the force supplied by the engine? Okay, so we're using one of the other expressions here for power. Power is equal to force times the velocity. So remember that comes from this derivation where we have our work equals force times parallel displacement. You sub that in for work in the power equation. And since you end up with displacement over time, you can call that velocity and sub that in, which gives you power equals force times velocity. So it's coming from that derivation. So if power is equal to the force times the velocity, then the force is equal to power divided by velocity. We are given 12 kilowatts, which is actually 12,000 kilowatts, or 12,000 watts. So that 12,000 watts divided by 8 meters per second gives you 1,500 newtons of force. A 24 kilowatt motor runs a vehicle at a speed of 8 meters per second. What is the force supplied by the engine? Again, you can use the expression power equals force times velocity. Rearrange it to solve for force is equal to power divided by velocity. This is given in kilowatts, so 24 kilowatts converts to 24,000 watts. Divided by the 8 meters per second gives you a force of 3,000 newtons. An athlete pulls a sled with a force of 200 newtons, burning 600 joules of food / caloric energy every second. What is the velocity of the athlete? So here we can use that expression where power is equal to force times velocity. Since we're solving for velocity, that is equal to power divided by force. We are given 600 joules per second. So that is our power right there. Remember, power is joules per second divided by 200 newtons of force. And that gives you a velocity of 3 meters per second. So letter A there. An athlete pulls a sled with a force of 100 newtons, producing 200 joules of thermal energy due to friction every second. What is the velocity of the athlete? Again, for this, we have our power is equal to force times velocity. Velocity, therefore, is equal to power divided by the force. You take your 200 joules per second divided by 100 newtons, and you end up with 2 meters per second. So letter A. A 3-kilogram block is initially at rest on a frictionless horizontal surface. The block is moved 8 meters in 2 seconds by the application of a 12 Newton horizontal force, as shown in the diagram below. What is the power developed when moving the block? So let's take a look. So power is equal to force times distance over time. We're given distance and we're given time. So technically that would give you velocity. So when you do calculate distance over time, there you have your expression power is equal to force times velocity. It's just broken down that way because that's what we're given. So if you take your 12 newtons of force times 8 meters divided by 2 seconds, you end up with 48 watts. The practice problems that relate to this lesson are the chapter problems number 79 to 91 and multiple choice number 26 to 30. Let me know if you have any questions on them, and they can be found on Google Classroom.